Hey. All right. Cool. Thanks, everyone, for coming. I see some team members in the house. That's cool. Thanks to Alex. I really enjoyed your presentation. I'm not sure if he ran out. Oh, cool. Really nice. And I was checking your site, but it takes a lot of effort. Okay, so blockchain scalability solutions. That's what I'll be talking about. A little bit about myself. My name is Leo. I'm from the Netherlands, so which explains the "ow" in my name. I studied electronic engineering, but have been doing software most of my life. I actually dropped out of school, which is like the cool thing to do now. I used to do virtual reality, that's my background, and virtual reality had a few waves. I would say we're now in the second wave. The first wave ended in the mid-2000s when everybody was giving up on virtual reality, and so did I. I worked a few years for Microsoft in Shanghai, and after Microsoft, me and my ex-Microsoft colleague, we founded Enuma in Hong Kong in 2015. What is Enuma? Enuma Technologies, we are a bunch of developers and we build stuff. We build stuff for, for startups, for enterprises, big companies. We do hardware, software, mostly software. And our first project in Hong Kong was a blockchain project, a blockchain hardware project. We made a hardware key for Ethereum and Bitcoin, and that was very interesting. So we got to learn about blockchain because our customer needed a solution, and so now using blockchains 3 years ago was very early, and so we have been getting a lot of expertise in the subject. So we do a lot of blockchain projects, blockchain-related projects, and one of them is building a decentralized exchange, and I'll share a little bit about what we've learned building that. I promise there's only one slide about actual blockchain. I'll keep it short. So, blockchain is a chain of blocks, makes sense. And how does it work? Well, every block has a hash of the previous block. And the hash of the block is just all the data inside the block. It's a bit like git commit, right? If you know a git commit, you get a hash, which includes the previous git commit hash, etc. And I think what Bitcoin was really innovating on was that nonce. Nonce means number used once. So there's one number, and it takes a lot of effort to find that number so that the hash is actually a small number. When you hash data, usually you get a 256-bit number, and usually that's a huge number, but actually it's still a number, so you can actually compare it, and if you want to be the hash like maybe small, maybe you want a hash that is smaller than 100 million, right? You have to try many times to get a small number. And so this is part of the innovation, and all the miners are racing to find that nonce, and the first one to find it and convince others gets a reward. And then what are the problems with that? So maybe you can see it. You have a single blockchain with blocks appending. So every miner is processing every transaction. You saw all those miners are racing to find the next block. So everybody is processing all those transactions multiple times. And all the transactions are competing to get into the block. So every time you are paying someone, right, with Bitcoin, or any other blockchain, you're actually competing with other transactions getting into that same block. And then that does sound a bit weird for a decentralized technology, right? If it's decentralized, then why am I waiting for the other guy? And all transactions are recorded indefinitely by every full node. So, there's a piece of data, your payment, it will stay in that data set forever. So what does it mean? That the data is ever growing and keeps growing forever and ever. And lastly, your transaction has to be picked up by a miner for it to be valid. So even though you have the money, right, you have Bitcoin or whatever crypto, and you can transfer it to someone, but you're waiting, you're still dependent on a miner to actually mine that transaction. And then the recipients have to wait for that mining. So the problems are very obvious, right? You have this data problem. The data keeps growing forever and ever. Ethereum is clocking in at 500 gigabytes now for mainnet, which is ever growing. There's a speed problem, right? Because everybody's competing for the same transactions to get them into the blocks. So Bitcoin famously 5 transactions per second, Ethereum 20, Bitcoin Cash 200. And so we were contracted, Enuma was asked to build a decentralized exchange, but the requirement was we have to get the same performance as a centralized exchange. Well, we look at NASDAQ, how many transactions does NASDAQ do, right? 10,000 per second. So, with Ethereum, you cannot even come close. Visa for payments is even more faster, I would say, 30,000. And that's the average, actually. So, with Christmas, they'll do much more. So, different solutions, different teams have been looking at different solutions. Bitcoin Cash famously increased the limit from 1 megabyte in Bitcoin to 32 megabytes. So that, they say, okay, if the block size limit is the problem, then why not just, times 32? And now suddenly we have a lot of capacity. And it's true, right? That's why they can do 200 transactions per second. Bitcoin Core went a different way. They said, there's a lot of crap in our transaction data. What if we separated the trivial, the important parts and the extra, and they call that signature data, witness data. And so in SegWit, they separate that data, and so they get a little bit better transaction speed, but it's not that much. And then what I'll be talking about today, there's a lot of layer 2 technologies. So, the Bitcoin, Ethereum, the blockchains are inherently inefficient, and part of that is actually a security guarantee. So instead of trying to improve the security of the blockchain or the efficiency of the blockchain, what if we do other technologies on top of the blockchain? And those are layer 2 technologies. Plasma, Cosmos, Polkadot. I think Joseph Poon from Hong Kong was involved in Plasma, I believe. So he says, okay, we can do a hierarchy of blockchains. Lightning, also Joseph Poon, I believe, right? Yeah, that guy has done a lot of good work. Makes a network of state channels, and I'll work through those two options. So what is a layer 2 technology? You have a layer 1, which is your blockchain. It's slow, it's inefficient, but it's there, it's secure. People use it because it's, it has some very strong guarantees. But then we make layer 2, and layer 2, the security is still dependent on the first layer, but layer 2 can choose whatever they want. They can choose a different algorithm, they can choose a different blockchain, different speeds, different block sizes. It can be limited to maybe only a few players, right? Maybe you can say, I'll do a healthcare blockchain, and I'll call that a layer 2. And then I do a separate payment blockchain, I call that a layer 2. And what does that look like? Now you get this view, you have our gray main blockchain on top, which is the slow, big one. And then we have a more efficient, light one on the bottom. And then, obviously you want some guarantees, so we can sync a hash, one of those hashes. We can tell the first layer once a day, this is a secure hash. This block was seen as valid, and so nobody can actually fake the data in layer 2, because you can go to layer 1 and actually see, look, I can see what happened on that day. A bit like, Git submodules comes close, right? Where you put a hash of another project into your main project. And then if there's a problem in that second layer, for example, the second layer, what's very common is that the second layer blockchain, they don't use proof of work. They'll use a different consensus algorithm, maybe proof of authority, where people vote on valid blocks, right? Instead of wasting a lot of energy, you can vote on a block. And you say, you know, there's 5 people that can vote, and if any block has more than 3 votes, then it's valid, something like that. But what if the computers are down and there's no vote happening? So then the blockchain is faulty and doesn't advance. Well, because you have some layer 1 to fall back on, these blockchains can still be exited. So they call that an exit because maybe there's some money locked up in layer 2, and then you can still get it out with layer 1. And then another approach of layer 2 is called state channels. And then how does that work? You still lose the main blockchain on top, the gray one, and you have some contract, some smart contract there, and then you can say, okay, I'm gonna open a channel with a person, and so that's a transaction that happens on a certain time, but in that channel I can trade off-chain. That means it's just between 2 people, nobody in the middle, there's no chain that I'm talking to, I'm not competing for transactions to get into a block, right? So finally, I can transact with someone without waiting for other people transacting. And so that's what the graph is showing here. We have a channel. In that channel, we can do peer-to-peer transactions. And then at some point, you can choose to close the channel. And then it goes back to the layer 1. And the channel is closed. So there's something very in common with both of these, right? There's a hierarchy. This is also a hierarchy. So does it look familiar, right? Actually, we already use this pattern in the real world, right? When I give cash to someone, I'm not waiting for the central bank to change numbers. Right? I can just give you cash, and you'll trust that the cash that you receive is actually valid. And the same with a contract. Right? When 2 companies, they enter into a contract, they'll trust each other. They don't have to go to the courtroom to fight that for every contract. They only go there when there's a dispute. Right? You know, when you don't pay me, then I go to court, right? And then, or I can go to the bank first, and then the bank can escalate. So this hierarchy actually is very, very common. We already have that in real life. Okay, so state channels. Right? We chose state channels as the solution for our decentralized exchange, but there are some problems with that. So, for example, each channel allows 2 peers to interact, and only 2 peers, right? I'll do a channel with you, and then we can trade, or we can do payments. But if I want to trade with somebody else, I'll need to have a channel with them. And then each of that still requires an on-chain transaction. So you still have that transaction that you're competing with, you have to pay for, is slow. A channel requires a deposit, right? If there's nothing at stake, then you can cheat in your state channel. So there has to be a downside to opening the channel, maybe a deposit or a collateral. And each channel has bookkeeping, right? All these transactions back and forth are no longer stored in the chain data, which is why the chain data doesn't grow, but you still have to keep track of that. So it is inefficient in different ways. And one solution from Lightning Network on Bitcoin, they use this kind of solution. They route these transactions through other state channels. So you have 2 guys here, the yellow people, they want to trade, or they want to do a payment, and they don't have a channel with each other, but there is a path through other people's channels. And so you can say, I give you a payment, but you have to promise to give it to the next guy, until the baker that is selling me the bread actually gets it. So this is one solution. And another solution is, why don't we say some of those hubs, nodes are actually special, and we call them hubs. And so you will open a channel with 1 or 2 hubs. You can see the guy in the middle has 2 channels open, but everybody else has a single channel. And we let the hubs take care of talking to each other, right? So this is much more efficient from a user point of view. You don't have to have multiple deposits, multiple open, closed transactions. You'll do it once, and then the hubs take care of that. And does this look familiar? Actually, this pattern also looks familiar, right? We do that for planes. You know, when you want to fly from one city to another, unless it's a big city, you'll have to connect through a hub. So I'm a big fan of seeing these patterns that appear in nature. They appeared in nature for a reason, right? This is biomimicry. And then, so if you see those patterns reappear in your software architecture, that's usually a good sign, right? And so this is what we chose to do. We made a decentralized exchange using state channels. And it looks like this, right? We will have users open a channel with an exchange, which is the big orange hub. And on that exchange, people can offer to buy or sell anything. When it's time to actually settle a transaction, you want to finalize this trade. It goes to the exchange first, and the exchange forwards it to the guy that is selling. Or possibly, you know, they can also aggregate the exchanges. They can forward between them. So only the exchanges have to have multiple channels open, and the users just open one channel. They only have one deposit, so also that is very efficient. Yeah, okay. And actually, if we go through, you know, what real-world analyzed data looks like, this is a graph that Mattis of the Enuma team compiled of real data of trades. And you kind of see these people, each dot is a blockchain address. And then the lines are trades. And you can see that there are clearly hubs in that picture. So there are nodes that are being used a lot of times for trading, especially the guy on the top, right? Looks like a hairdo. So, yeah, it's a very natural model to follow. And we get the question often, what is your transaction speed? If you have this kind of architecture where you have peer-to-peer trading, what is the transaction speed? Well, it's hard to tell, right? Because there's no longer a single database that we have to write to. You know, a blockchain is a distributed database, but it's still one of it. So everybody's competing for that same transaction. And now that is no longer the case. So what is the transaction speed really depends on what two people can communicate on this over the internet. Yeah, so I'm glad I was a bit faster than planned, because I think lunch is next, and I don't want to be the guy keeping you from lunch. But we have time for questions.
Yeah, anyone want a question?
Oh yeah, there was a question over there.
Oh, sorry. I want to ask that when you are having something like a payment channel, it requires the receiver to be always online in order to update his record he keeps. Does it make is it a problem for your application? And if so, what is the solution for this?
Oh, actually, very good question. Yeah, I'm not sure if everybody understood. When you're trading with another person, what if the other guy is not online? In the case of a blockchain, you can just write to the blockchain because it's there. But if you actually have to, you have a channel with another person, you have to give them the transaction directly. But if he's not online, he cannot receive the transaction. So there's actually active research on that topic. And so we're working with a researcher called Patrick McCorry, yeah. And one of the solutions that he came up with is you can actually appoint delegates to monitor those transactions on your behalf, and they get a little fee in return, right? So some of the nodes, they might actually be online because they can collect fees when you go offline. And so this is just a way to incentivize people to monitor transactions on somebody else's behalf. So there's a lot of research to fix exactly that problem. Yeah. Good question.
Okay. Any other questions?
I want to ask how actually the layer 1 and layer 2 different blockchain get synced. Like Bitcoin didn't have smart contract, how do it really works?
Well, yeah, good question. So I showed a slide where different blockchains were syncing. Yep. Actually, even Bitcoin supports instructions. It's just very limited, right? So even in Bitcoin, you can store arbitrary data. So you could still have a child chain and then with a block hash and post it as a arbitrary data in the Bitcoin blockchain. You know, the Bitcoin blockchain has instructions, and some of them are like op return. You can include any data. It can be any hash, and that is good enough to to prove that your child chain had a certain state at a certain time. Yeah, very cool. Another one next.
Hi. One of the problem of the blockchain of the Bitcoin, I believe, is the auditing things and how this going to comply, how to keep the secret because everything is publicly accessible in the database, right? And how can we control and reverse the transaction or freeze accounts, those things? How could we solve in the new technologies?
Yeah, good question. So on something like Ethereum, you can still solve that, but you would have to explicitly program it, right? You can use zero knowledge snarks, like zero knowledge proof, to do a transaction where on the chain you can't actually see who got what. So you can do that. When you use a payment channel, actually the transactions are completely private, right? When I pay you, I guess it's like giving you cash. Nobody knows. But of course, if there's a dispute, and then you go to the to the courtroom, or you go to the blockchain, then everybody knows, hey, this guy didn't pay or whatever, right? So as long as you're in the channel, all the transactions inside the channel, they stay private between the two people. So that is another reason, another way to prove that. Another question. Almost lunch in 3. Okay, yeah, thanks everyone. So I'm from Enuma. We're always looking for talented developers. So we are a Hong Kong-based company. We have a booth here, so happy to chat more about the projects that we're doing, or this in particular. Yeah, thanks everyone.
Thank you. Yeah, and I would like to thanks for all the speakers and sponsors. And also, don't forget to visit their booth and enter into the draw so that you can get a prize. Thank you.